Hello, my friends. Welcome back. In the previous videos, we were talking about different techniques that we can do to improve the throughput and then the latency. And then the last topic that we talked about was how we can improve the timing. And we looked at a few different techniques, actually, two. We looked at the parallel structures, right? And we also looked at, I think, adding another layer of registers, right? Yes, so we talked about adding register layers and the parallel structures. For example, in the previous video, we talked about how we can divide an 8-bit multiplier into four 4-bit multipliers and then like concatenate the results with proper shifting, obviously. And we saw how we can actually improve the timing. In today's video, I wanted to talk about the third technique, right? Which would be flattening the logic structures. So let's copy this code so we don't have to redo the whole thing again. And we go here, just gonna paste it here, and I'm just gonna go flatten logic structure. Okay. Um, this would be something else, but well, anyway, let's just get rid of these because so as I said in like some of the previous videos, not every technique is suitable for every design. So we cannot really use the power thread design that we had and just like apply this technique to that because it just doesn't work. Like this is not a technique used for that design. Um, but we can do something else. We can come up with a different design so we can actually see how we can do things here. So let's call it I don't know. Let's call that um, read write. We want to write to a register, right? Based on some control signals. So what happens is that like the concept of the flattened logic, like when we talk about flattening the logic structures, is like very closely connected to the concept of parallel structures, right? That we talked about in the previous video. But the only difference is that it is specifically used to address logic sequences that are interconnected due to some priority encoding, right? So most of the time, the synthesis and layout tools such as the Intel Questa or AMD, the Vivaldo tool, right? Those are usually smart enough so that they're capable of duplicating the logic so that they minimize the fan out. But most of the time, like 99% of the time, they're not smart enough, so they don't have the ability to deconstruct the logic sequences arranged in a linear manner, right? And also, they do not possess sufficient insight into the design's priority constraints. All of these will be clear when I start talking about this, right? So let's say that we have this design. There is an input clock, and there is input data. We call it I data. And let's have like another input, and I just like want to make it 4 bits so it's easier. Um, this is also 4 bits and CNT control, right? We'll just call it control for now. So based on the values of the control, I want to assign something to my output data, right? We actually don't even need this. Let's keep it as simple as we can. So what I want to say is that at every rising edge of the clock, right? What I want to do is to go if first I'll show you like how we can do that without using this technique. And then obviously I'll show you how you can do this with using the flattening logic structure technique, right? So I want to go if I control 0 equals 1 tick b 1. So if bit 0 is 1, right, then I want to do something. I want to go just like keep it in mind for the sake of simplicity. O data is 4-tick bit 0001, right? Or I don't know, something, anything, right? I'm just gonna call that, I don't know, like I'm just gonna call that 1100. So if that is 0, that the least significant bit of the control signal is 0, is 1, then I'm assigning this value to O data, right? And then I want to go else if, and then I want to copy this, and let's just keep it clean and clear. If bit number 1 is 1, then let's just copy this and put it here. O data would be, I don't know, any value you want. It's just like an example, right? And then I'm just gonna copy this 2 more times, and then go if 2 was 1, and then if bit 3 was 1, and then here we can just go 0, 1, and then here we can go, I don't know, all ones maybe, right? So this is the first design. So I'm deciding on the value of O data, like what I want to assign to O data based on the control input that comes in, right? And this is, as you can see, like if we implement this design, it's going to be a priority encoder. It looks at the first bit, like the bit 0, and if it's 1, then it does this and it doesn't do anything else. If it's not 1, and then it goes to the next statement and see, okay, what I need to do. So if we implement this design, you will see that the synthesizer, right, most likely 99.9% of the time is going to implement a priority encoder, right? Another extra layer of logic that sits there because you coded like a this. But another way of doing this thing, right, is assuming that the control signals are mutually exclusive. Again, see, that's what I mean. Like you cannot use every technique for every design and be like, oh, I want to use the flattened logic structures for this design. It simply may not be applicable. And as I said, this is specifically used for like when you can't get rid of the priority things, right? Anyway, so I'm just going to copy of this, right? Comment this part out and then go down here. And assuming that the control input is mutually exclusive. So either like at every time, one of these 4 bits is 1. We cannot have like 2 1s at the same time, right? So we can just do it like this, as simple as that. We can just get rid of the else statements, right? And then do it like this. Be like, okay, if that's the case, like if this is true, then do this. If this is true, then do this. If you implement this design, then you are not going to see a priority encoder, right? So it's a simpler design and you improve the timing a lot, right? And then the other technique that I wanted to show you here, well, not technique, just like small things here and there that help you have like a cleaner code, is to get rid of like equals 1. So when I go here and say if I control 0, it means like if that condition is true, which means that if that bit's equals to actually bit number 1, right? Like a logic value high. So that's basically the same thing. And so this is one way of doing that. And then you can also do it another way, right? It's a cool way to do that too. I'm just going to show you if in case you wanted to do that. So I want to go case, right? And I control. And then the first case is 4-bit 0001, right? And then if that's the case, then I want to do this. Okay. And then you can just copy this and then go down here, be like, if it's 10, then we do this one. Okay. And then we can just bring these two guys back. And if it was 1 0 0, and if it was 1 0 0 0, then we go. So here is 0 0 1, and then here is the 1 1 1. Okay, so that basically does the same thing, right? And then here for default, so you can, okay, let me tell you this. You can do this, and it basically does the same thing. It's like a case statement, right? Similar to this implementation, not really different. It saves you a lot of delay in your timing. And so it's saying if I control as this, then do this. If it's that, do this. And like you can have an extra logic for default that says if it's not any of these cases, so like when you have more than one bit set to high, right, at every time, then you can do something about it. Go O data is, I don't know, 4B 0 0 0 0, for example, which is like different from this. Like the functionality of these codes are not the same, because if you give 0 0 0 0 this code, it doesn't really know what to do with it. It doesn't assign anything to O data because it doesn't fall into any of these, right? But I'm just saying, like, if you use the case statement, you can do this, or you can get rid of, like, if you're sure that you're not going to get like any value other than these 4, then you can change this to default, right? And just get rid of that, for example, and then go 1 1 1 1 here, and it does the same thing. So if it gets a 0 1, it's that. If it's get a 1 0, it's that. 1 0 0, it's this. And by default, it's set it to like getting 1 0 0 0, and it sets it O data to this value. Anyway, this is what I wanted to talk about in today's video. Again, this technique is not applicable for all designs, just like any other technique. And you can only use that when you're addressing logic sequences that are interconnected due to some priority encoding, right? And you need to have like some considerations as well. So for example, here we know that the I control is coming from a block where, I don't know, somehow we're getting this, like, let's say it's an address decoder or something, right? So that we're sure that like it's mutually exclusive and we're not going to get like more than 1 bit high at any time. Anyway, that's about this technique. If you learned something new, if you like this content, please like the video. And if you haven't already subscribed, please do so. It helps me a great deal. And thank you for watching me again. And see you all in the next video. You guys take care. Bye-bye.